with the last talk today. So,
Let's talk more about it. Yeah, I'm sure we can.
Yeah. No, I'm just waiting for these guys. Okay, so for our last presentation, we'll have Leïla talk about grain growth in olivine melt systems, and we'll see some of her experimental results.
Thank you, Lars. So this work was done during my PhD thesis. It was supervised by Emmanuel Gardes and Fabrice Gaillard, and I've been collaborating with different people. David Siffré, who is a PhD student of Fabrice Gaillard as well. Luis Morales, who is in Potsdam and with whom I did the EBSD measurements, and Jacques Pressigo, who is also in Orléans, and who has also helped me to perform the EBSD measurements. So thanks to Uli's presentation, I'm going to talk about grain size and grain growth. Well, with all the talks that have been given since yesterday, grain size seems to be an important parameter, mainly through the permeability, which helps understand melt segregation and can be implemented in two-phase flow modeling. But it also gives insight on the seismic observations that we have of the mantle, and also it can help out with rheological experiments where sometimes stepping strain rate experiments are performed, and it is important to know what's the grain size during the experiment at a known strain rate or stress condition. But most importantly, why does grain size singularly matters? Well, we need to upscale from human length and time scales to geological length and time scales. So I'm going to talk about static grain growth. So when I say static grain growth, it's done without any deformation processes. Because Uli was stating previously that grain growth is not static, it's a dynamic system, since the grain size is continuously evolving. And so to continue on that, there are two types of grain growth mechanisms. The first one is normal grain growth, where if we plot the distribution of the grain size, we can see that it shows a unimodal distribution, and that with increasing time, this distribution does not change. So it's a continuous process which shows a uniform coarsening of the microstructure, which is opposed to abnormal grain growth, where we can start out with a unimodal grain size distribution, and as time increases, then we have large grains that are going to develop at the expense of the small grains forming the matrix. And if we continue on with time, well, we can get back to this normal grain growth process. So it's a discontinuous process where large grain develop at the expense of the small grains forming the matrix. So I'm going to talk mainly about normal grain growth. So what is usually done in experiments is that we use a sample that has an initial grain size distribution. We anneal this sample, so we make the grains grow. Then we get the sample out, we measure the grain size, we check that the distribution is, of course, unimodal distribution. And then usually what is done is that we try to fit it to this Arrhenius form here equation, where G is the grain size. So my grain size is not a D, it's a G. Where the final grain size to the power n minus the initial grain size to the power n is equal to a temperature and time. It's a temperature and time dependent process. So what is usually done is that n is empirically determined previously to the rest of the equation. And so by determining this grain size exponent, we know what kind of process is happening that is controlling the grain growth. And in the literature, I found that usually the final grain size minus to the power n minus the initial grain size to the power n as a function of time can help us determine the temperature dependence. And then this equation here, this Arrhenius equation, is then used to extrapolate from experimental to geological length and timescales. Now, I had to constitute a database, since there are previously published experiments where they investigated static normal grain growth. And so, well, I've already explained this, where they annealed at high temperature polycrystalline olivine samples, measured the initial and final grain size, and determined an empirical grain growth law. And so, from my literature research, I started out with Carotto's paper, which was published in '89, where he looked at single-phase polycrystalline olivine aggregates. But he also investigated different effects, like the water effect. And then this paper from Nichols and Mackwell in '91 investigated the oxygen fugacity effects, as well as secondary phases like pores. And the melt effect has also been investigated. Also, one of these papers is from Udi Faud. And the pyroxene effect, where there's a certain mechanism known as Zener pinning, has been investigated. Now, if we look at this database, the temperature goes from 1200 degrees to up to 1450 degrees, and from atmospheric pressure to 1.2 GPa. And the duration of the experiments can go up to a month. And by looking at the grain size exponent, what we see is that it's constrained between 4 and 5. In some cases, it can go up to 9.2. So this is an extremely high grain size exponent. So I've looked at the average grain size exponent, and I've plotted the data here in this plot, where you have the grain growth rate as a function of reciprocal temperature. So here, these data points are from the literature, where you can see the dry, so water-free grain growth. And if we plot the other samples from the literature, melt-bearing and water oversaturated conditions, you see that they show higher grain growth rates. So we have two regimes. We have one first regime here, where dry atmospheric olivine samples present slow growth rates, and a second regime where we have fast growth rates. And so that's how my talk is going to be divided into these two sections. So I'm going to start out with the slow growth rates. So here is the same kind of plot, where we have the grain growth rate as a function of reciprocal temperature. And so we have two kinds of experimental samples. First of all, we have the gray samples here, the gray data points here, which represent synthetic forsterite. And in green, we have naturally derived olivine aggregates. And so we can see that there's a same global trend, where as we increase the temperature, the grain growth rates increases. And the grain sizes from these empirical laws, grain size exponents from these empirical fitting were determined between 2 and 9.2. Now, by looking at all these data, I found that there was a systematic problem on the grain size exponent, which will have a significant impact on the other terms of the Arrhenius law. So we need a good theoretical background to constrain the grain growth law under dry conditions. So that's what I'm going to present to you now, the theory behind grain growth. So grain growth occurs by the migration of grain boundaries, which make the microstructure evolve. Now, well, a grain boundary, we've been talking about it since yesterday. It's the interface transition between two crystals of the same phase with different crystallographic orientation. And so here you have an example, a schematic of two crystals separated by a grain boundary. And so the microstructure is going to evolve with this atom here on this side of the grain boundary, which is going to go through the grain boundary and then attach on the other crystal there. Grain boundaries are also high diffusion pathways. And grain growth is known to happen due to a minimization of the Gibbs free energy of the system. So there are three possible driving forces that control grain growth. So the reduction of the curvature of a grain boundary. So this grain boundary here, as the crystal will want to minimize its interfacial energy, the curvature is gonna reduce. Another possible driving force is gonna be an externally applied pressure, or also a chemical reaction from a chemical gradient. So I started out with the Burke and Turnbull analysis in 1952, which states that the radius of the grain as a function of time is equal to the driving force times the grain boundary mobility. Now the driving force is equal to the chemical gradient over the grain boundary width, but also to the pressure gradient, which includes the curvature of the grain boundary over the grain boundary width here. Now I've taken the rate of grain volume change and found that this same dr over dt is equal to the flux time time omega, which is the not molar mass, which is another interesting parameter, over the stoichiometric factor of the growing grain. Now, if we look at Fick's first law, so the flux, it's a function of the fusion, but also the chemical gradient potential. And so by substituting all these equations, we end up with two types of equation, where the grain size exponent here is constrained at 2 for diffusion within the grain boundary, whereas the grain size exponent is 3 if we consider lattice diffusion. So I've looked up in the literature to see how these diffusion coefficients were the behavior of these diffusion coefficients. So here you have diffusion as a function of inverse of temperature, and these lines here correspond to the diffusion coefficient of grain boundaries. So green magnesium, blue oxygen, and black silica. So it's a temperature-dependent process. And here in this plot, I've considered that the grain boundary width is equal to 1 nanometer, which is the structural grain boundary width that Uli was showing previously. And so if we look at lattice diffusion coefficients, we see that they're orders of magnitude inferior to grain boundary diffusion. So I've re-implemented these diffusion coefficients in the equations that I've presented. So here is the grain growth equation, which is a function of the grain boundary diffusion. And in this plot here, you can see a grain size in micron as a function of time. And as you can see, the grain sizes increases drastically. Here for a temperature of 1200 degrees Celsius, pressure of 1 atmosphere, and an initial grain size of 2 micron. Now, if I plot the lattice diffusion dependent grain sizes, you can see that the grain sizes are way below in respect to the grain sizes which are grain boundary diffusion dependent. And so to know which kind of diffusion coefficient I should be using, so namely whether it's grain boundary or lattice, I've added in this plot the experimental grain sizes that were the final experimental grain sizes that were determined for these conditions here. And as you can see, none of these fits correspond to the experimental grain sizes. So I've assumed that the grain boundary width must have another value. And if I plot here the grain boundary width of 10 nanometers or 100 nanometers, you can see that for approximately 10 nanometers, the experimental grain sizes are really well constrained by this fit here. And so by using least square regression on my database, I was able to determine that the effective grain boundary width on which the fusion effectively happens is about 13 nanometers. So it's quite different from the structural grain boundary width, which is of 1 nanometer. And so to know if my model was correct, if this equation is the one that we should use, I've plotted the calculated grain sizes here as a function of the measured grain sizes. And as you can see, the grain sizes are relatively well constrained by this equation. So under static and dry conditions, we can well reproduce the final grain the experimental final grain size that are measured. So what I've done is I wanted to compare all the models that had been published in the literature, namely, so they were those that were fitted with the empirical grain growth law. And so as you can see, these two curves here that correspond to Hiraga's and Tasaka and Hiraga model do well reproduce these experimental grain sizes, whereas the grain growth equation from Carato shows really slow and almost null grain growth until high duration. And Nichols and Mackwell seem to exaggerate the grain growth, the grain sizes. Now, if we look at this plot, we can see that the model fitted with the equation based on grain boundary diffusion predicts huge grain sizes for big geological timescales. Now, I would like to emphasize that extrapolation to geological timescales must take into account secondary phases such as pyroxene melter fluids, deformation processes where dynamic recrystallization is known to decrease the grain sizes, and probably also water, which can be easily implemented in this kind of equation when we know the water effect on the grain boundary diffusion coefficient. So now that I've explained the atmospheric database, I'm going to talk more about the fast growth rates, where we see that fluid and melt-bearing aggregates show higher grain growth rates. So these experiments done here exhibit high melt contents, so 2, 4, and 47% melt, and also water over saturated conditions. So I decided to do another set of experiments under high temperature and high pressure with melt contents varying from nominally 0 to 80% melt. So to do so, I started out the experiments with San Carlos olivine and a basaltic melt, which was H2O and CO2 free. And so I decided to use 5 different melt contents, nominally 0, 1, 2, 12, and 80% melt. And I've also performed 2 experiments under water over saturated conditions with 2 weight percent and 20 weight percent. But I've also performed one synthetic grain growth experiment, which showed genuinely melt and water-free conditions. So namely forsterite, which was salt gel based. So what I did then was to anneal the San Carlos crystals in CO2 furnace at the FMQ buffer. So this is experimental jargon for those who are mathematicians. At 1100 degrees Celsius and for 15 hours in order to get rid of most of the impurities that were contained in the San Carlos. These crystals were ground to relatively small grain sizes, so they were by performing the BSD measurements, I determined that the initial grain sizes were 5 or 10 microns. So it's pretty big compared to what has been done in the literature. And the samples were then placed in gold palladium capsule to try to minimize the iron loss effect. And I varied the pressure, the temperature, and the duration. So the pressure varied from 0.3 GPa, 0.5 GPa, 1.5 GPa, and 3 GPa. Temperature range from 1200 to 1350 degrees Celsius, and the experimental durations were run from 1 hour to 15 days. So for all the experiments that I performed, I tried to place the capsules within one piston cylinder assembly. So namely, if I had 4 melt contents, I would place the 4 capsules. But as I will show you later, I didn't see any melt effects. So for a wide range of pressures and temperatures, I've only used 2 different melt contents, namely 0 and 1%. And I would like to point out that the piston cylinder assembly used talc. And so this talc is known to diffuse hydrogen during the experiment and exchange its hydrogen with the iron, thus producing water inside the capsule. And that could create some problems, namely increasing the water content in the sample. And well, water has been shown to increase grain growth. So to just check the water contents of the sample, as I will be showing later, I've performed FTIR measurements. So for the grain size determination, as I was saying, I did EBSD measurements with Jacques Pressigou and Luis Morales. So I have acquired 2D images of the polished surface of the sample, which measured the crystallographic preferred orientation. And so the grain boundaries are clearly visible with this kind of method. And then I used OEM data analysis and image SXM for grain size determination. So I'm going to show you how I determine the grain sizes. So I acquired unique grain map. So it doesn't show here, but this is normally full of different colors where each unique grain has a different color. This map was then segmented with image SXM, where I used an edge detection and median filtering technique. And then I skeletonized and pruned this image here, and I superimposed this image to the image quality map that the OEM data software gave, which showed, so in dark, the grain boundaries, and in lighter color, the interior of the grain. So by doing so, I then manually cleaned the artificial edges and holes, because this technique is not automatic, unfortunately. So for each sample, I had to double check that all the artificial edges and holes were indeed gone. And then I created a binary image that I then used in image SXM to get the surface area of each grain. Then the surface area was was used to determine the grain diameter by considering that each grain was a sphere. So for all the samples, I've acquired between 100 and 1270 grains in order to get a statistical a grain size distribution, which presented a normal grain growth distribution. So I'm going to continue now with the microstructure results because I think it's quite important that I present to you the nominally melt-free samples, so those in which I did not add any melt. So as you can see here, so for high temperature and high pressure conditions, so 1350 and 1.5 GPa, well, maybe those in the end of the room cannot clearly see, but there's a melt pocket here and there's a melt pocket here. So these nominally melt pockets are really nominally, these nominally melt samples are nominally, they contain melt, so they're not genuinely melt-free. And this was systematic. So for another temperature condition here, 1250 degrees Celsius, I've found melt here. And for lower temperature and pressure conditions, I still found melt in these nominally melt-free samples. Now, if I look at different melt contents where I added here 1 weight % melt, well, we can see here a melt pocket, there a triple junction. And I didn't go to high enough resolution to determine if the grain boundaries were wetted or not, because I wasn't concerned with wetness. Yeah?
Which of these marks is 20 microns? There are too many lines.
It's the whole, from there to here. This is 20 microns. Yeah. And so for 12% melt, well, these melt pockets just increased. And here is the same thing, 12% melt, but for a longer duration than the picture just underneath. And well, I've determined that the melt is heterogeneously distributed. Now the water oversaturated samples presented weird textures. Weird, not really, but so the porosity is really high, which indicates a fluid. Which indicates that the fluid was present during the experiment. But also I have spinel that crystallized during the experiment. So here this is for a condition of 1200 degrees Celsius and 0.3 GPa. And for higher pressure conditions, I also had orthopyroxene that was precipitating in these samples. Now, as I was saying earlier, I used talc piston cylinder assemblages. So I had to measure the water contents, and I used the 80% melt samples to determine the water contents. And well, I determined that the melt water contents was inferior to 2 weight % water. Now, I'm emphasizing here the melt water content because all of the water that might have been produced within the capsule would have gone inside the melt. Now, this is below the melt solubility threshold, and which means that there is no free water at grain boundary. And so now let's go to grain sizes. So here I show you a plot, not grain growth rate, but final grain size minus initial grain size, and here I've deliberately implemented a grain size exponent of 2 as a function of time. Now, this is for condition at 1250 degrees Celsius and 0.5 GPa. And as you can see, well, grain size increases with time. There doesn't seem to be a dependence of grain growth melt on the grain growth kinetics. As you can see here, you have a wide range of melt contents, and they seem to present the same grain sizes. I've also plotted the dry atmospheric fit that I've presented previously. That's here in black. And as you can see, the liquid-bearing aggregates present bigger grain sizes than under melt-free conditions. Now, if I look at higher temperature, 1350 degrees Celsius, which was a condition under which I've annealed the salt gel sample, so the genuinely dry and melt-free olivine aggregate, we can see that it's relatively well fitted by the dry atmospheric grain growth equation. Maybe I should emphasize that here for the diffusion coefficient, I've used the pressure effect that was determined in the study of Fay et al. So that I could simulate dry grain growth at a pressure of 1 GPa. And if we look at these data points here, we can wonder, is there really a pressure effect? Well, we can eventually think that there's a small pressure effect. This is a sample that was annealed at 1.5 GPa, and this one here is at 3 GPa. So if we plot this data as a function of pressure, well, we can maybe say that for liquid-bearing sample, there is maybe a small effect on grain size, and that it may be due that this effect of pressure may be an indirect consequence of its effect on wetness. So there was a study from Yoshino et al. In 2009, I think, which showed that the dihedral angle change will decrease with increasing pressure. But maybe we can talk more about that, Uli. So now that I've had my experimental grain sizes, what's interesting is to get a grain growth equation, right? So I'm going to talk now a little bit about the theory in case of liquid-bearing aggregates. So there's a well-known theory, which is known as Ostwald-Ripening, or the LSW theory, for the authors who wrote down this theory. So it states that for crystals dispersed in a secondary phase matrix, whether it's solid or liquid, the difference in surface area between the small grain here and the large grain here is the driving force for grain growth. And so this leads to a difference in solubility. Now, there are two different mechanisms in Ostwald-Ripening. So there's diffusion-limited grain growth, but there's also interface reaction-limited grain growth. And so I'm going to start out with diffusion-limited grain growth in the case of the secondary phase being a liquid. I'm not interested in solid secondary phases. So this is the classical expression of diffusion-limited grain growth. And so the grain size exponent here is 3. It takes into account the liquid diffusion, the concentration in the liquid, so interfacial energy. But I found that there was something missing, right? Because if we're in the case of diffusion in the liquid, then we would expect the same kind of form as in grain boundary limited, grain boundary diffusion limited grain growth, where we have the grain boundary width here that's in the equation. So I decided to employ the same formalism as I've presented earlier in the atmospheric grain growth theory, where starting with the Burke and Turnbull analysis in 52 with the same kind of equations, so driving force, mobility, chemical potential, and pressure gradient. The rate of grain volume change, which leads to the same equation here. Fix first law, and then re-implement that. We get here the grain radius variation with time, which is a function of liquid diffusion, liquid concentration, but also the liquid width between two grains. So I've considered two cases. One case where delta L is way inferior to the grain radius, and one case where delta L is superior to the grain radius. Now, in this case here, the melt fraction is the volume of melt over the grain volume, right? And so it becomes a function of grain radius and liquid width. And so we get this kind of equation where we have a grain size exponent of 3 and the melt content here that's in under diffraction. Now, if the liquid width is bigger than the grain radius, then we get this kind of relation between delta L and phi and R, and we get once again a grain size exponent of 3 and these grain sizes, which are a function of the melt content. Now, this is in the case where we consider melt films around the grain. But as we've seen on SEM images, it's not always the case. We can have melt within triple junctions there. So what I did is I looked into the paper of Yasuko Takei and Sash, their paper of 2009, where they determined a pressure gradient as a function of the grain radius and the melt content, then reinserted that in the driving force here, and I get this final equation where the grain size exponent is here of 2. We have liquid diffusion here, and this term that here, so the melt content, the liquid width. And so for diffusion limited, in case of liquid diffusion limited grain growth, we have these 3 sets of equations. Now, I've told you that there was also a second mechanism in Ostwald-Rippening, which is interface reaction limited. And the equation that's generally accepted in the literature is this one, where we have the dissolution rate at the liquid crystal interface that replaces the diffusion of the liquid. So the grain size exponent here is of 2. So to sum up, here are all the equations that I'll be using to try to fit the experimental grain sizes. And you can see that the grain size exponents are either of 3 or 2. So now to head back to the experimental data, we can see in this plot grain growth rate as a function of inverse temperature. Here this line is dry normal grain growth. Here are the experimental, the previously experimental grain growth that were measured. The boxes here are the experiments that were H2 oversaturated in my study, and this box here corresponds to the grain sizes measured from nominally melt-free to 80% melt. So, as I've stated in the introduction, the grain growth rates, whether it's melt or fluid-bearing aggregates, are faster than dry normal grain growth. However, we see that there's a large scattering of the experimental grain growth rates, which is not predicted by the theory. So, I've hypothesized that it might be due to wetted and non-wetted grain boundary migration. So, the grain growth rate, the grain growth rate equation should have this kind of form, where we have psi, the contiguity. So it's the same kind of contiguity as Sash was presenting, but so psi, and which is times dry normal grain growth rate plus wetness times liquid normal grain growth. And so here are the fit to the equations that I've presented earlier, where I take into account wetted grain boundaries and non-wetted grain boundaries. So here is dry normal grain growth. This box here corresponds to the final experimental grain sizes that I've measured in my study. Grain size as a function of time, right? And here, this blue curve there corresponds to this equation here, where I simply assume that delta L is fixed. And so I fixed it at 25 nanometers. And so you can see that this fit here cannot explain the experimental grain sizes. So let's move on to the other set of equations. So the green here, where we consider delta L inferior to the granular radius, or that delta L way superior to the granular radius. So with these equations here, and as you can see, grain sizes are higher than what our experimental observations show. So then let's move on to triple junction and fixed delta L. So I'm going to start out with 25 nanometers. And as you can see, the grain sizes predicted by this model are higher than experimental grain sizes. So I tried to do the same thing, but with a bigger, unrealistic delta L, so 1 micron. And as you can see, we're starting to approach the experimental grain sizes that we observe in this study. And so if we try to fit the last equation that I've showed you from the theory, which takes into account the dissolution rate at the crystal liquid interface, well, you can see that it plots here. And it's still too big. The grain sizes predicted by this model are still too big than the experimental grain sizes that we measure. So I decided, so is this really dissolution? Why wouldn't it be precipitation, right? Why would we consider that dissolution and precipitation have the same kinetics? And I've looked into the literature, and maybe somebody here can tell me. And I found no justification as to show that they had the same kinetics. So I've decided to take the grain sizes determined in my study and fit an empirical law, which here is termed Kp, which correspond to the precipitation rate at the crystal liquid interface, and re-implemented that in this kind of equation where we have contiguity and wetness, and get a final grain growth law where the grain size exponent is of 2 and is dependent of diffusion of silica at grain boundaries, the effective grain boundary width, and also the precipitation constant that has this form here. And so I'm going to end with this final plot where you have grain size as a function of inverse temperature. So I fixed the pressure at 1 GPa. The duration is 360 hours, and initial grain size of 1 micron. And so here you have the dry normal grain growth fitted with the atmospheric database. And with this equation here, if you add just 1% of melt, you have a huge jump in grain sizes. And as you continue to increase the melt, the liquid content, so here 10, 30, and 100, well, the grain sizes don't increase as much as this initial jump here. And so here's the take-home message. So we can see from the literature that there are 2 grain growth regimes. There's one that is slow and dry, and there's a second one that is fast for liquid-bearing aggregates. In both cases, the grain size exponent is 2. So this is the most important message that I want you to get, because I spent 3 years trying to determine this grain size exponent, and finally I found that it was 2. So the grain size exponent is 2. So the dry grain growth can be constrained with diffusion at grain boundaries of silica. From the atmospheric database, I've constrained that the effective grain boundary width is approximately 30. So it's a factor 30 above over the structural grain boundary width. And the atmospheric, so the dry regime can be fitted with this equation here. Whereas for liquid bearing grain growth, it's limited by interface reaction and not diffusion limited. And it's due to precipitation rates at the crystal-liquid interface. And we have the wetting behavior of the liquid phase that's included in the fast grain growth rate regime. And so you have the equation that is right here that takes into account contiguity and wetness. So thank you very much.
All right, time for questions.
So, my turn? Yeah, okay. So, if there is a diffusion and then there are two interface steps and a diffusion step in between.
Yeah.
So I guess my first question is that all these diffusion coefficients are diffusion along the grain boundary,
Yeah.
but your grain growth occurs by diffusion across the grain boundary. So is that the right diffusion coefficient to put into the, right? I mean, you showed it at the beginning that you just need to move the atom from this side to that side.
So you're talking about whether it's perpendicular or parallel diffusion? Yeah, so, yeah, well, I had to take, that's something I wanted to write in my thesis, right, where the diffusion, I wanted to put a little perpendicular sign next to the diffusion. Unfortunately, in the literature, I didn't find any perpendicular diffusion within the grain boundaries. So, yeah, I had to fit it with the
I don't think there's
silica grain.
What you get it from is your grain growth measurements. So. And maybe it's the same thing, I don't know.
Yeah, maybe it's the same thing, but I would expect it not to be the same thing intuitively.
My other question is I'm a little bit, no, I'm very confused. Not by you, but I just haven't caught up with what you've done. But so you're saying that the interface step is limiting.
Yeah.
And when you have
liquid,
present?
yeah.
And
So whether it's melt or fluids.
right. So what's limiting is the slowest step, right? So that means the fusion must be quite fast.
Yeah.
Must be faster. So why do you get faster grain growth if the diffusion step?
Because the diffusion coefficient for, anyway, the melts that I've been using in my study is so high that it cannot predict the experimental grain sizes.
So there's a different diffusion coefficient.
Yeah, yeah. So I took the slowest, which is I think silica, because I thought that anyway the grains on the other side of the liquid will have to grow once all the atoms were on that side, right? It cannot grow as long as there are atoms missing and that are on the other side. So I took the slowest one. Yeah. So it was, I think, silica.
I might have misunderstood something on one of your earlier slides. You showed the size of the triple junction increased, the grain growth rates went down.
No, so the only thing I changed was not the size of the triple junction, it was the liquid width. So yeah, diffusion has to occur over a bigger width. So 25 nanometers was smaller than...
Oh, those are completely wetted grain boundaries.
Yeah, so it's completely wetted grain boundaries, but I have the wetness parameter. Is it? Yeah.
Right. So you said triple junction, and 1 micron is slower than for...
So it's not the size of the triple junction, it's the size of the liquid width along the tubes, I think. So yeah, I'm not sure right now. I think I missed.
Actually, I didn't understand that quite. Is it like a Hashim treatment type thing where the grain is completely coated by? Because I wasn't quite able to figure out what that delta L is from the figure you
Yeah, so in the case of here, inferior to R and superior to R, yeah, I think it's as in the Hashim-Strickman case. Yeah. But here I'll have to double check to answer your question. Because I think the size of... Yeah, no, I'm not going to try to answer if I don't know right now.
Other questions?
I do have one. Can I have one more question? Sorry. I know you all want to get a beer, so I should talk quickly. But so the dry case is the sol gel case. Is that right?
No, it's based on the atmospheric database that I
Okay.
presented earlier. So it's synthetic and natural mixed up.
Okay. All good. All right. Well, let's thank Leïla one more time.